Welcome to Tech Disruptions, deep dives into the technologies reshaping industries, from AI to quantum to biotech. Let's get into it.
For years, the gold standard for quantum computing's promise was this idea of quantum supremacy, the point where a quantum machine could perform a task no classical computer could manage. Google famously claimed it in 2019 with its Sycamore processor, stating it solved a problem in 200 seconds that would take a supercomputer 10,000 years.
And that 10,000-year figure was precisely the kind of headline-grabbing metric that set the bar. It implied an insurmountable gap, a qualitative leap in computational power that classical machines simply couldn't touch.
But now, a group of researchers has seemingly dismantled that claim, not with a more powerful quantum computer, but with something far more pedestrian, a standard laptop. A single CPU, not a server farm, not even a high-end gaming rig. A laptop beat a multi-million-dollar supercomputer on its own benchmark. That's the core of it, isn't it?
That's exactly right. The Caltech team, led by Yunqiao Liu, Adam Buland, and Alexandru Georgiou, essentially found a fundamental vulnerability in the problem Google chose to prove its supremacy. They demonstrated that an ordinary laptop running a cleverly designed classical algorithm could solve the same task in a matter of minutes.
That's an astonishing claim. It feels like someone just showed up to a Formula One race with a bicycle and somehow won because they found a shortcut nobody else noticed. How did Google miss this? Or perhaps more accurately, what exactly was this quantum supremacy problem, and why was it supposedly so hard for classical machines?
The problem Google used was what's called random quantum circuit sampling. Imagine you have a complex quantum circuit, essentially a sequence of quantum logic gates, and you run it. Each time, it produces a probabilistic output. The goal of this specific problem is to sample from that output distribution. To put it simply, you're trying to figure out what results the quantum computer is most likely to produce, and then generate those results yourself. Google argued that generating these samples, particularly for a large enough and complex enough quantum circuit, was computationally intractable for classical machines.
So it wasn't about simulating the entire quantum computer or solving every type of problem. It was a very specific, rather abstract task, predicting the likelihood of certain outcomes from a quantum process.
Precisely. And this is a critical distinction. The original classical estimates for the difficulty of this problem often focused on a full state vector simulation, meaning trying to perfectly calculate and keep track of every possible quantum state the system could be in. That's incredibly resource-intensive, requiring exponentially more memory and processing power as the number of quantum bits, or qubits, increases. It's like trying to map every single atom in a hurricane to predict its path.
Which is why the 10,000-year supercomputer estimate came about. They were aiming to perfectly replicate the quantum system's behavior with a classical machine.
Exactly. But the Caltech team realized something crucial. You don't need to simulate the entire quantum circuit perfectly to sample from its output distribution. They found a shortcut. Think of it like this. If you want to know what kind of leaves fall from a particular tree, you don't need to model every single branch, every photosynthesis reaction, and every air current. You just need a mechanism to produce a statistically representative sample of leaves. The Caltech algorithm does something analogous for the quantum circuit outputs.
So the zip file analogy from the research title really makes sense here. It's like Google was trying to send an uncompressed, massive data file, and this team found a way to compress it down to a tiny fraction of its size without losing the essential information needed for the task. What was the core of this compression? What was the trick that allowed them to sample so efficiently?
The key was exploiting what they call structural properties or symmetries within the random quantum circuits Google used. Many of the earlier classical simulation methods treated these quantum circuits as completely arbitrary, highly entangled systems, which made them incredibly hard to simulate. However, the Caltech team developed a randomized algorithm that leverages a technique known as tensor network contraction.
Tensor network contraction sounds like a mouthful and probably a very complex mathematical operation. For listeners, what does that actually mean in practice?
Conceptually, a tensor network is a way to represent the complex relationships between different parts of a quantum system. Think of it as a diagram where lines connect different mathematical objects, or tensors, representing parts of the quantum state. Contraction is the process of simplifying this network, reducing its complexity. The Caltech team didn't invent tensor networks, but they applied them in a highly optimized and randomized way specifically for the sampling problem. Instead of trying to perform an exact deterministic contraction, which is still computationally intensive, they found a way to do a probabilistic contraction that could still generate accurate samples from the distribution. It's like finding a statistically sound shortcut through a very dense mathematical forest.
So they weren't aiming for perfection, they were aiming for good enough to solve the sampling task. And good enough turned out to be orders of magnitude faster. This isn't just a minor improvement. The difference between 10,000 years and a few minutes on a laptop is astronomical.
It absolutely is. Their algorithm essentially sidestepped the exponential memory and processing wall that full simulations hit. By focusing purely on the sampling task and cleverly using these tensor network techniques to exploit the circuit structure, they could achieve comparable results to Sycamore in a time frame that renders the original supremacy claim for that specific problem moot. This wasn't about building better hardware, it was about building a better algorithm.
That's a crucial distinction. It speaks to the idea that the quantum advantage isn't just about raw computational power, but about the interplay between the problem, the hardware, and the algorithms, both quantum and classical, that are brought to bear. This makes the goalposts for quantum supremacy seem incredibly shifty, doesn't it?
It really does. This incident profoundly redefines what quantum supremacy means, or perhaps more accurately, highlights its fragility. The moment Google announced their achievement, the race was on for classical computer scientists to find a counter-algorithm, and they did. This isn't the first time such a challenge has been made either. IBM, shortly after Google's announcement, also published a paper arguing that a classical supercomputer could solve the problem in a matter of days, not millennia. But the Caltech result takes it a step further by demonstrating it on consumer-grade hardware in minutes.
So quantum supremacy becomes less about an absolute fixed point where quantum computers definitively surpass classical ones, and more about a moving target. As quantum hardware improves, so do the classical algorithms designed to mimic or even outmaneuver them on specific tasks.
Exactly. It's an arms race between two different computational paradigms. Quantum computing proponents often choose problems that are known to be hard for classical algorithms, but hard is a relative term. What's hard for today's classical algorithms might be trivial for tomorrow's, especially if someone finds an elegant mathematical shortcut. This means that for a quantum supremacy claim to truly hold up, it needs to be incredibly robust against future classical algorithmic improvements, or it needs to be on a problem that is verifiably and fundamentally intractable for classical machines.
Which implies that the specific random quantum circuit sampling problem chosen by Google was perhaps too contrived or too specifically tuned to highlight quantum strengths without sufficiently guarding against a clever classical counterattack.
That's a fair assessment. The problem was designed to be difficult for classical computers as they were then understood, and to showcase the entanglement capabilities of a quantum processor. But it might not have been sufficiently robust against novel algorithmic approaches. The problem definition itself, or the assumptions made about classical limitations, proved to be the weak link. It's not that quantum computers are fundamentally incapable, but that the benchmark chosen was susceptible to being solved in a way that wasn't initially foreseen.
This raises a bigger question about the future of quantum computing. If these supremacy benchmarks are so easily overturned by clever classical algorithms, what does that mean for the actual practical applications of quantum computers? Is it all just hype if their biggest victories are so easily reversed?
It's certainly a setback for the narrative of quantum supremacy as a definitive, unchallengeable milestone, but it doesn't invalidate the entire field of quantum computing. Quantum computers still hold immense theoretical promise for other types of problems, where their unique properties like superposition and entanglement offer a genuine, provable advantage. Think about problems like factoring large numbers, which underpins modern cryptography, or simulating molecular interactions for drug discovery and materials science. These are problems where classical algorithms hit fundamental theoretical roadblocks, not just practical ones that can be circumvented with a clever trick.
So the message isn't quantum computing is dead, but rather that it is important to be more precise and less hyperbolic about what quantum computers are actually good for and how that advantage is measured.
Precisely. This incident is a crucial reminder that the focus needs to shift from chasing abstract supremacy benchmarks to demonstrating verifiable, practical quantum advantage on problems that are genuinely relevant to scientific and industrial challenges. It forces researchers to ask harder questions. Is this problem fundamentally hard for classical computers, or just hard for the current classical algorithms? And can a quantum algorithm provide a provable speedup that isn't easily mimicked by a classical shortcut?
It also underscores the often underestimated power of algorithmic innovation. The focus often becomes the hardware race, more qubits, faster clocks, sometimes leading to the oversight that a truly elegant algorithm can often achieve more with less.
Absolutely. This is a testament to human ingenuity in classical computation. It's a reminder that even against the backdrop of seemingly insurmountable quantum advantages, the landscape of classical algorithms is constantly evolving. A clever mind, armed with a deep understanding of the problem structure, can still find ways to achieve what was previously thought impossible with existing classical hardware. It's less about brute force and more about elegant design.
So what should listeners take away from this zip file that broke quantum supremacy? What are the key insights here?
First, the definition of quantum supremacy is extremely fragile and relative. It depends heavily on the specific problem chosen and the state of classical algorithms at that precise moment. Second, algorithmic breakthroughs in classical computing can profoundly shift the perceived boundary of quantum advantage, often at a fraction of the cost of new hardware. Third, this isn't a death knell for quantum computing, but a crucial call for more rigorous and practical benchmarks. The field needs to focus on problems where quantum advantage is robust and less susceptible to classical workarounds.
And finally, it's a stark reminder that the race for computational power isn't just about building bigger and faster machines, but about smarter ways to use existing machines.
Indeed, it's a challenge to both quantum and classical researchers to constantly push the boundaries of what's considered computationally feasible.
So the next time a claim of quantum supremacy is heard, should the first question be what classical algorithm was used to compare it against, and how sure are the researchers that someone won't find a shortcut?
That should absolutely be one of the first questions. The burden of proof for robust quantum advantage just got significantly higher.
That's all for this episode of Tech Disruptions. Join us next time as we keep exploring the technologies reshaping our world. Thanks for listening. We'll see you next time.
Stay curious out there.